So good morning, Dr. Whale and Associates. Today I'm going to be talking to you about my research project, sodium-ion battery feasibility for renewable energy storage in a residential setting. This has been my research project for the last 5 months, and my supervisor, Manicum, has been a really big help in compiling all this research. So just to get straight into it, for the content today, there'll be background. So why do we need storage? Battery storage. So what is it? Sodium and sodium ions. What do they mean in the grand scheme of things? Current residential storage systems that are currently available. And moving into aims and objectives of the research project. And then the bulk of this presentation will basically be about the electrodes and electrolytes of sodium ion cells and what they have to do with the big picture. And then safety, cost and market feasibility with some concluding remarks. So as a background, the first part is why storage? So why do we need storage? And I suppose if we go all the way back to the beginning, we talk about the use of fossil fuels. So fossil fuels are anything that's burnt for energy. So we use it for our electricity. If you don't have solar panels and you're connected to the grid, a lot of that energy comes from fossil fuels. And these fossil fuels create greenhouse gases. Some different types of greenhouse gases include carbon dioxide, methane, fluorocarbons, and nitrous oxide. So greenhouse gases can lead to the polluting and heating of the Earth's atmosphere, and we call this global warming and or climate change. So this is a big part of the media at the moment. So the reason being is because global warming has negative impacts on different ecosystems. So it can cause things like melting ice glaciers, sea level rising, heat-affected species survival, increased invasive species, and other things like coral bleaching. So mining for fossil fuels destroys ecosystems by clearing land. So that's another negative impact it has on the environment. So renewable energy is the most probable solution to this. Renewable energy can come from things like the sun, so that's solar, and then wind energy. There's also hydro. So why haven't these particular types of energy been used? Why aren't they the primary energy sources for us currently? Well, this is because they're intermittent. And this basically means that they're not always there and they're not always reliable. So that's one of their downsides. So moving into battery storage, the reason we need battery storage is for what I just mentioned, because the sun is not always shining, the wind's not always blowing. These renewable energy sources need to be stored. So when it's not occurring, the sun isn't shining or the wind isn't blowing, we can access this energy still. So currently, lithium-ion batteries are on the market. So a lot of people have heard of Tesla batteries. But they're quite expensive, so a lot of people can't afford them currently. And they're not exactly environmentally friendly. So, yeah, batteries tend to store energy in the following way. So energy inside a battery is stored in chemical form. So it comes from these energy forms like wind and hydro that spin turbines and create energy and then get stored in chemical form inside the battery. And then when they're needed, they get released in electrical form. So these batteries go through a process called oxidation and reduction. So these will switch from one electrode to the other depending on what's going on. So whether there's a charge or a discharge cycle happening. So when a battery's at work, electrons move from the cathode, which is the positive electrode, and they move through a medium called the electrolyte to the anode, which is the negative electrode. So just a little bit of background on sodium and sodium ions. Why do we focus on sodium or sodium ions in this study? Well, basically lithium is quite expensive and it's not very abundant. So to look for the next best option, we're looking at one down from lithium. So lithium on the periodic table there, what we can see is just situated at number 3. So sodium is situated underneath lithium. So it is the next lightest alkali metal. So it's basically the next best option to lithium, and sodium is very abundant. So that is a positive attribute about sodium. So sodium sits at number 11 on the periodic table, and it's recognised as Na+, a positive element, capable of forming ionic bonds, and they can form ionic bonds with chlorine, and this is a great component for electrolytes in some batteries. Unfortunately though, as stated, sodium is a little bit heavier than lithium, and this is a downside to sodium. So current renewable storage systems that are available at the moment are the Tesla battery. So these lithium ion batteries are already on the market, with new versions coming out quite soon, I believe. They're very high cost though, and this is something that's not feasible for a lot of people. We've got the Aqueon saltwater batteries. These were actually imported in Hawaii. However, the company went bankrupt. That's that middle picture there. We've got solar reserve design. That's that bottom picture with the molten salt towers and thermal solar panel array. So you've got all those thermal solar panels around the edge. And then we've got that molten tower in the middle. So basically the salt is heated to very, very high temperatures, over 1,000 degrees, and energy is able to be stored inside those this salt. And then there's NGK, which have created a sodium sulfur battery using liquid electrolyte and ceramic plates, which is a Japanese company. So moving on to aims and objectives, the research question basically that we've focused on here is sodium ion battery storage for renewable energy a feasible option for residential purposes? And there's very little literature on the topic. So therefore the objectives have to be broken down in a few ways. So concentrating on, is sodium a good alternative to lithium ion storage and why? And the next four questions create sort of a scenario for us to test with the literature. So does the current anode material in study complement the sodium ions in the cathode material enough to compete with lithium ion batteries? Number two, do these possibilities lead to an equivalent efficiency to lithium ion battery technology? Number three, does sodium ion compare or outweigh cost and safety features of lithium ion? And number four, does sodium ion battery technology currently have a good market outlook before lithium ion residential storage floods the market? So getting into the bulk of the research that has been done, electrodes and electrolytes were the main focus to see if there was any sort of any efficient or cost-effective materials that could see lithium become second best in any way. So we first focused on the cathode. So the positive electrode of the battery is positively charged, and sodium can be used for this because sodium is a positively charged element. So for these battery cells, sodium is a great component to be using for the cathode. So the problem doesn't really arise within the cathode, it's more the anode. And the reason for this is because the cathode has sodium, whereas the anode, because of sodium's size, it's very difficult to be taken up by the anode. So sodium is a lot larger than lithium, as I've stated, and harder to be taken up. Lithium alkali metal has an atomic radius of 152 picometers, and sodium 227 picometers. So it's quite a bit larger. Therefore, it's really hard to be taken up by the anode. And ordinarily, as we move into the anodes, it's just good to know that lithium-ion batteries usually use a graphite carbon. However, as we stated, sodium is quite large and can't be taken up by these materials. So this is a real problem. So some other materials that have been studied include metal oxides, and we've got a few listed down the bottom there. As you can see, copper as an oxide and nickel as an oxide. And we've also got manganese dioxide there. It's one of the more popular anode materials being studied currently. And then there's phosphorus and other alloys such as tin and antimony. So Kunda D et al. Have stated that hard carbons, for example, prepared by pyrolysis of sucrose, and the most studied negative electrode materials for sodium-ion batteries. They achieve reversible capacities of up to 300 milliamps hours per gram, which is quite good, but we've actually seen through the literature that there is better materials out there for use. So they've tried to use nanotubes and nanoflowers to increase intercalation with sodium. So some studies have achieved between 400 plus milliamp hours per gram. And this is after 1,000 cycles as well, which is a really great result. And alloys have been used for sodium with tin, and they show 878 to 758 milliamp hours per gram. This is just at the initial discharge and charge, however. And then phosphorus seems to have the highest reversible capacity there, so 1,800 to 1,900 milliamp hours per gram. So I guess the question is, why are we not using these materials currently? And the answer is basically there's a few downsides, and one of the main ones is volume expansion. So when you're using things like phosphorus and you're having these reactions going on inside the cell, they basically form other compounds. So, eventually you get this volume expansion. And if you have something like tin with sodium, it's estimated to be around 420%, which is a lot, which is quite a lot. It's a big volume expansion, and it's not ideal for a battery to be having such a high volume expansion. So they've come up with some solutions. This can be avoided with materials such as aluminium, as they do not form alloys. However, they produce a lower operating voltage. So you've got this back and forth between, should we use a cheaper material and get a lower voltage, or should we use these more efficient materials and have this volume expansion? It's a real problem for sodium-ion batteries at the moment. So then you've got the electrolyte, and one thing to note with electrolytes is it's very difficult for people to study electrolyte feasibility, because you can only really study them with the cathode, and this is because the anode hasn't been agreed upon with sodium-ion batteries. So it's something that is a bit of a roadblock. So electrolyte is basically something that the electrons pass through from one electrode to the other. So that's that middle part in that picture there. The electrolyte of choice must be stable and create a good ionic conductivity. Electrolytes can be in either aqueous or non-aqueous form. So firstly, looking at the non-aqueous electrolytes, a non-aqueous electrolyte is an electrolyte that contains non-aqueous solvent, so it can be a liquid still. It just can't be containing that aqueous solvent. So can be in the form of ceramic, gel polymers, glass, or organic crystals. So in terms of, and just quickly to note that these studies were done with just agreed a cathode, so the anode was not taken into account in these particular studies. So gel polymer electrolyte had a capacity shown to reach 964.1 milliamp hours per gram. Other promising non-aqueous electrolytes that are currently being studied include ethylene carbonate and sodium perchlorate. The original founder of the lithium-ion battery also notably is trying to work on a solid-state sodium-ion battery currently. His name's John Goodenough. So he's obviously realising that sodium-ion batteries are definitely the next step forward in battery storage for renewable energy. So his is not it isn't workable at the moment. It's still in prototype phase, but it's very interesting to see the progression of that. So aqueous electrolyte is in a liquid form using water as a solvent. So this is a cheaper option. Basically, you can use things as simple as seawater. The problem with aqueous electrolytes, however, is they have a high volatility. than that of non-aqueous electrolytes. So this usually happens between metallic electrodes and liquid electrolytes. So the solution they've come up with this is to use ionic liquids. And these are preferred. And if you look over the table over here, they've used a few. They're showing what aqueous electrolyte does with different cathode materials, its specific capacities and cycles, which is very interesting. So it's, again, the drawback is the anode material is not agreed upon. So these results are purely just cathode to electrolyte studies. So moving along with the safety of the sodium ion batteries is something that is really pushed. So it's said that sodium ion batteries are a lot safer than lithium ion batteries, and this is true in one sense but not in every sense. And just to go through this, lead acid batteries, for example, contain toxic or carcinogenic materials. Sodium ion batteries can be recycled for the most part. Lithium ion batteries have a potential for explosion. A lot of people would remember the Samsung Galaxy phones exploding, and not being allowed on planes and things like that. That's because lithium ion can only be stored at around 30% minimum. Otherwise, it has that risk of explosion. Whereas sodium ion batteries can be stored at zero charge, so they don't need any charge to be stored, which is one of its biggest safety features. Solid state batteries are a lot safer than liquid because of the volatility, and also they can remain stable under high temperature increases, which is another great feature of the solid state battery. And in that picture there, we've got the liquid and the solid state. So in terms of cost is another thing that sodium ion batteries are really praised for. So because sodium is so abundant on the Earth, it makes up about 2.36% of the Earth's crust, which far outweighs that of lithium, which is only about 0.0017% of the Earth's crust. Sodium is also found in seawater as well, so its abundance is very high, meaning that the cost is low because there's a lot of it. So cheap materials for electrodes and increased efficiency will assist in the cost being a desirable feature. So salt water is cheap, obviously, but as we were saying before, liquid electrolytes are volatile. So then we've got the aqueous electrolyte, cheap, that's what I just mentioned. And so you can basically create a really cost-effective battery through using some of these methods. It's not just that sodium is really abundant, but the efficiency is somewhat lapsed when you have these cost-effective materials such as the liquid electrolyte and things like that. So in terms of market feasibility, currently I thought I would just start off with Whitaker, a statement from them saying that it is predicted that the global annual market for stationary storage will exceed $30 billion by 2021. So this is basically saying that, lithium ion is in a good place to be infiltrating the market quite largely at the moment, especially if government got behind it. So that's only 4 years away, not even to 2021. So if sodium ion batteries don't become up to scratch with lithium ion batteries currently, there might not be a place for them in the market for quite some time. Basically, it's taken lithium ion batteries more than a decade to get to this residential storage phase. They've been around for a long time. And that's not just to say that they couldn't get there, it's just hasn't been a focus. So studies and prototypes are being brought out. However, they are not ready for commercialization as the efficiency has not reached an optimal level. And this is sodium ion batteries' biggest problem is efficiency. And when they do find efficient materials, it seems to have some kind of drawback. The other problem is government. So government policy changes, not focusing on the environment as much anymore. We've seen in the government that they've cut a lot of cost. And so if you don't have that investment into these particular inventions, then you're not going to have a push forward for them. So if government policy changes happened, this might assist. Acquion just went bankrupt. That's just one example of investments going wrong. So in conclusion, just a few statements. Efficiency standards have been reached. However, problems in cyclability and volume expansion raise issues. Cost-effective materials don't always yield enough efficiency for market permeability. Lower cost batteries with liquid electrolyte are too volatile for residential use. High functioning temperature batteries are also not optimal for residential use. Sodium ion batteries may not infiltrate the market before lithium ion batteries dominate. And government policies and investments are not currently focused enough on environmental issues. So this puts a lot of pressure on sodium ion batteries. I just want to finish with some of my thoughts on the topic that I found through reading the literature. Basically just to state that people are not going to buy a cheap battery that is more environmentally friendly if it's not as efficient as a lithium ion battery. So people want that really good long-term investment. People aren't going to choose, unfortunately, the environment over a good investment. And that's just how, economics work and things like that. So, however, lithium's low abundance may, over time, be the key to sodium ion batteries' dominance. So over time, sodium is much more abundant, and when lithium deposits start to be depleted and prices start to increase, hopefully by that stage sodium ion technology will be really up there with lithium ion batteries, and therefore I do believe in time sodium ion batteries definitely have that feasibility to become renewable energy storage for most residential settings. Thank you for listening. If you have any questions, please let me know.